So let's keep talking about the graph algorithms. And today we're gonna introduce the search algorithms in the graph. So in the last time, we have gone through the basics for defining the graph data structure, and they represent it with the two ways, which is the adjacency lists, right? Adjacency lists is basically an array of lists, okay? And each list is for the adjacency vertices for each vertex in the graph, okay? So basically, the adjacency lists, you can think of it as some attributes of the graph. Basically, you can use g dot adj to include to access all the adjacency lists. And because it's an array, so you can use g dot adj of u. So this u is any vertex in the graph, and this will let you access all the adjacency vertex for the vertex u here, right? And I think for most of the algorithms, including the breadth-first search and depth-first search that we're going to talk about today, we'll use the adjacency lists as representation. But I think the two representations, the second one is the adjacency matrix. Okay, these two are basically equivalent. The difference is that they have different memory, different efficiency in memory use. Like if the graph is very sparse, you may want to use adjacency lists as opposed to the matrix representation. All right. Okay, so we'll talk about the search algorithm. We'll start with the breadth-first search, and I don't think we will have time to cover both algorithms today, but we will finish the BFS first. And for the depth-first search, it is more, how to say, a more advanced algorithm. So we will look at several different versions of depth-first search. We will start with the simpler ones, and we may have time for, or we can introduce the full version or the advanced version for depth-first search, which uses more, which basically describes the topology of the graph with more details, and also which means that full version or advanced version of DFS will be the basis for other algorithms that we're going to cover that we're going to cover in this lecture for basic graph algorithms. All right, so we'll start with the search algorithm. So the searching is basically refers to the process that we should systematically follow the edges, right, in order to visit the vertices of the graph. Okay, and it will return the structural information of the graph, and it is basically the heart of all graph algorithms. So the first kind of searching is called breadth-first search. The second one is depth-first search. And the breadth-first search, let's lay out some notations, right? Still, this G equals V of E is the short expression to represent a graph, right? And because it's a search, we need to start from somewhere. So we'll use the source vertex S as our starting points, the source, right? And the BFS will explore the edges to discover every vertex reachable from S. Okay, so some vertices may not be reachable because it's not guaranteed that all the, it may be the case that some vertices are isolated, right? So we need to be careful about defining whether some vertices are reachable from the source. Okay. And this BFS will compute the distance from the source, right? From where we start to all the reachable vertices. And the distance here, right, is defined in terms of the number of edges. Okay, you know, the edge is the line that connects two vertices, right? And we know that from the last lecture that some edges may be associated with the weights, right? And that weights can also mean the distance. But this is not the case for this BFS search algorithm. In the BFS, in the simplest BFS, we are not considering the weights of the edges, but the distance that we define here is only about how many edges that takes to go from the S to that vertex, right? It's defined purely on the number of edges between. Okay, it's not about the weights of the edges. Okay. And the results of a BFS is some tree structure. It will produce a Breadthfirst tree, okay, and in that tree, the source vertex is the root, okay, it is the top node of the tree, okay, and in that tree, we can go from the root, which is our source, right, and to any node in that tree. For example, we have a node of V, right? That's also a vertex in the graph. So the simple path between the root node S to that node V, it corresponds to the shortest path from S to V in the graph. Okay, so that is our expected results. Okay, so the path in the tree corresponds to the shortest path from S to V in the graph. Okay, and again, this shortest path is not defined against the weights of the edges, but it's just shortest in terms of the fewest number of edges used to connect these two vertices. All right. Okay, so where the name is from. So it's called Breadthfirst because the algorithm will follow such a principle that it will discover all the vertices at a nearer distance. For example, at distance k from S, before discovering any vertices that are farther away. Like before we discover any vertex at distance k+1, we will make sure that all the distance within all the vertices within distance k will be discovered first, right? So that is called Breadthfirst. We go as broad as possible. Before we go any deeper, we would make sure that we have reached all the vertices nearby first. Okay, so we'll have three types of vertices defined by this Breadthfirst algorithm, BFS, and we use three colors: the white, the gray, and the black. Okay, three kinds of vertices, and all the vertices will be initially white. Okay, so the white color indicates that they are not discovered yet, and a vertex will become non-white. It can be gray or black, but as long as it is non-white, then it means it is already discovered. Okay, so it will, the first time that we discover any vertex, it will become non-white. Okay, so that means either gray or black ones are already discovered. Okay, but there's also a difference between the gray and black. So basically, for the gray vertices, it may have white vertices in its adjacency list, or it may have adjacent white vertices, which means it has white neighbors, right, directly connected to the gray ones. But for the black ones, all the adjacent vertices are discovered. There is no white vertices connected to the black vertices. So it's just a metaphor to use the color, the scale of the color to indicate whether whether vertices are have been already discovered. And you can think of the gray ones as the frontiers between the undiscovered vertices versus the discovered vertices. Okay. All right. So next slide. Okay, we are not yet about the pseudocode yet, and we will first look at the outcome of the algorithm. We will basically construct a BFS or Breadthfirst tree, okay, and in which the root is the source vertex S, okay, and assume that a vertex U is discovered, right? What BFS does is basically to scan the adjacency list of U, okay? So we will basically use some for loop to go through the adjacency list for U, right? And during this process, because we are scanning the adjacency list, whenever a white vertex is discovered, then we will add an edge from U to V to the tree. Okay, so that tree is grown incrementally, right? When we are scanning the adjacency list of a vertex U, whenever a white one, which means that node, which means that a vertex is not discovered yet, we will add the edge to the tree. Okay, and so we can call it, because both U and V are now in the Breadthfirst tree now, and in the tree structure, by our convention, we can call the U as the parent or the predecessor of V. Okay, and we need to note that a vertex is discovered at most once, right? So when it's first discovered, the color will be changed from white to non-white, right? So the next time we meet this vertex again, we will know that it's already discovered. It's not a new vertex. So there will be only one parent to each vertex in the tree, to each node in the tree. All right, so let's look at the procedure, okay? We have 18 lines of code, and if we first look at the overall structure of it, right? So we can spot two. There's a for loop here, right? There's a big while loop here, and within the while loop there is another for loop. Okay, so it's basically a double nested for loop, right? And one thing we can notice is that there is a data structure that we used, and remember we have revealed the basic data structure for the queues, right? So this queue is a first in, first out data structure. So we will use this queue to store all the vertices. And also the queue will be the condition for the while loop, right? So this while loop will keep running until the queue is empty, right? As long as it's not empty, then the while loop will keep running. Okay, let's look at the functions for each blocks of the code. So yeah, so some additional information about the attributes of all the vertices. We have, of course, the color, right? We need to mark whether it's white, black, or gray. And also, the second attribute, D, is also important. It's short for distance, okay? So the distance marks how far away the current vertex is from the source, right? Remember, we give a source to the algorithm, right? It is wherever we choose to start from, right? And the third attribute is .pi, and this .pi is a convention for representing the parents, okay? So I guess here we should use not u.pi, but u, because u.pi means the parent of u, okay? All right, so given these three attributes, we need to first, right, we need to initialize everything properly, right? Because in the previous page, in the previous slide, we said every vertex will start out to be white. So we will basically use this for loop to paint all the vertices white except for the source. And the distance will be also initialized to infinity because we haven't started the computation yet, right? Once a vertex is visited, we will change that distance to a non-infinity value. Okay, and also the parents is initialized to non-values, right? Right, and the next step is to paint the source to gray because it is the first vertex we visit, right? It is where we start, and the distance is 0 because it's itself. The distance from itself is 0. Okay, and the parent is none because it has no parents vertex. Okay, that's initialization, right? So far, it's very straightforward. And the next two lines of code, right? We said we define a queue, right? And it's used to store all the gray vertices. Okay, the purpose of it is to right. So in the first run, in the first line, immediately after S is painted to gray, right? We can see that we initialize a queue and insert that S to the queue. So within the queue, it contains all the gray vertices. So the usage of it is to manage the set of gray vertices. So we will see that within the while loop, there's DQ, right? There's a InQ. So this DQ and InQ will will continuously scan all the vertices and then InQ the adjacency vertices into the queue again. Okay, so that queue will be will be utilized as a first in, first out data structure. So at the one end, we are dequeuing vertices, and meanwhile, we are inqueuing all the adjacency vertices towards the other end, right? Okay, so we will have a simple example in the next slide. So let's go through all the code here. All right. So the while loop will not end unless as long as there remain gray vertices in the queue. Okay, as long as the queue is not empty, right? So if you look at 11, the line 11, it will take the queue out, right? Remember, in the queue we have a head and tail, right? It will take a gray vertex out of the head of the queue, right? And within the body, so after that, that head element is taken out, we will execute this for loop, this inner for loop, right? And this inner for loop is where we explained in the previous slide that we need to scan the adjacency list of that vertex, right? We use the for loop to go through all the adjacency lists of U, right? So these G dot adjacent with brackets U will return the list that will return the adjacency list for the vertex U. We will go through all the vertex in that list, and we will check for each vertex to see if its color is white, right? If it's white, then it means it's a new vertex. It's been never visited before, right? If this is the case, then we need to change its color, right? Our goal is to visit all the vertices. So when we see a non-visited, it's not discovered yet. So we will change its color to gray, okay? And then we will increment the distance for V, right? We will change the distance of V, okay? Pay attention to the right. It's not V dot D, but it's the U dot D plus 1, right? Because that is because we start from U, right? We we look at the adjacency lists of U, right? And every vertex in that adjacency list is the neighbor of U. So because we start from U and we visit V, so in the BFS tree, the V will be the child of U, right? We start from U and we reach V, so V will be the child of U. So the distance for V should be the distance of U plus 1, right? Because we visited U first, okay? So, and then the relationship between V and U is that because we visited U, then first, so the U will be the parent for V, right? We go from U to V, so V will be the child and the U will be the parent, okay? And as soon as this is done, the V becomes gray, right? So remember, the loop will manage all the gray vertices, right? All the gray vertices. So we have new gray vertices created, right? Which is V. So we need to in-queue that gray vertices back to the queue. All right. So after all the vertices, all the adjacency vertices of U are visited, then we need to change the color of U, right? Remember, in the previous slide, we said that the difference between gray and the black is that the gray ones can have white neighbors, right? But the black one cannot have white neighboring vertices. So after all the adjacency vertices of U has been discovered, then we need to change the color of U. It's no longer a gray one, it's already a black one, okay? All right, so that's the BFS explained. So there's a interesting property of it is that the queue should consist of the set of gray vertices at any point, okay? So because if you look at within the if condition, at the line 14, whenever we paint a vertex gray, it will be in-queued at line 17. This is inevitable. Like whenever we create some new gray vertex, it will be in-queued. So no gray vertex will be skipped, okay? And also, whenever a vertex is dequeued at line 11, and in parallel with line 11 is line 18, it will also paint black, right? So whenever some gray one popped out of the queue, it will also not skipped. It will be changed to black, okay? So these two parallel mechanism makes sure that everything in queue is the gray vertex. It contains all the gray vertices. All right, let's look at an example. Okay, its a graph looks like this, right? We have 8 vertices from RSTU, VW, XY, right? And we start from S. So the number in the nodes, the number in the vertex is the D property, the distance property, indicating the distance from the source, okay? And because all the vertices are initialized to infinity, it looks like this, right? So that's after the initialization, right? So in the next step, we'll look at how the algorithm runs, because the queue is initialized to only one vertex, which is S, right? We need to dequeue it first, right? After S is dequeued, right? We will visit the adjacency list of S, right? So in the graph, we can see that the R and the W are adjacent vertices to S, right? So they will be visited, and that means their color will be changed to from white to gray, and their distance will be updated to 1, right? Because the distance will be the s dot d plus 1, and the s dot d is 0, right? So their distance will be 1. Okay, so here in this case, the order of inqueuing W and U are arbitrary, right? We didn't say any specific rule of which one should count before which, but we will see that if we specify some rules, the results will be different, right? But it's okay. It's basically the same process that we'll go through, right? So assume that we enqueue W first. So W is now at the head of the queue. And so next, the W will be dequeued, right? And we need to go through the adjacency list of W, right? So here we should notice that when we go through the adjacency lists of W, well, let's look at the previous step. So when we go through the adjacency list of W, and how many adjacency vertices are there? You can see there's S, T, and X, right? There are 3 adjacency lists, 3 adjacency vertices. So that's why this if condition is necessary, right? Because the S, the black vertex, is also listed, it exists in the adjacency list of W. But we don't need to go through S again. It's already visited, right? So we will need use this if condition to focus only on the white vertex, right? So we will find that it's vertex T and X, right? So these 2 white vertices will be painted to be gray, and their distance will be the distance of W plus 1, which is 2, and their parents. So within the final tree, W will be the parents of X and T, right? Because the way that we visit T and X is to start from W, right? We have such a direction. We start from W and visit T. Okay. And these T and X will be dequeued. All right, and then let's look at the next step. The next step is, so we just focus on the head of the queue. So the head of queue will be R, right? So this R is right here, right? So you can see that the principle of Breadthfirst is like after we visited W, we have enqueued some T and X, but we will not go deeper along this T or X, but we will go back to the upper level, which is the R vertex, right? Because we haven't finished all the distance within 1 first, right? We need to go through, go back to R first. So this Q data structure allows us to preserve this distance information and makes sure the Breadthfirst search will happen. Okay, let's look at the next one. After R is visited, then the V will be enqueued, and the distance of V is also 2. All right, and then we need to go back to the T and X. T will be dequeued, and the adjacents of T includes W, X, and U, but since only U is white, okay, so the U will be enqueued, all right? But now we will not stay at U, but we'll go back to X because we need to finish the distance 2 first, right? X will be dequeued again. X will be dequeued, and the adjacency of X, the white adjacency of X, which is Y, and it will be enqueued, right? And then we go to V, right? The V is the last one that is in distance 2. But since V doesn't have any white adjacency list, adjacency vertex, it will be directly dequeued. Okay, and the remaining U and Y will be dequeued because there's no adjacency vertex, no white adjacency list vertex. and after all, everything is dequeued, and the queue becomes empty. Okay, so that is a whole process of the Breadthfirst search. So since we have recorded all the parent relationship and the distance into the node, so now you can imagine that if we think of this S as the root node, and if we plot it in a just like a tree structure, right? So then R will be here and V will be here, right? It's a very typical tree structure, and I guess I will plot it in a 2 slides later, right? So it's a tree plot. That's if you look at the path from the tree, path within the tree, from the root to each vertex in the tree, we can it's the number recorded within the node indicates the shortest path from within the graph. Okay. All right. So that's it for the BFS, and let's look at the running time of the BFS algorithm. So when we analyze the code, we can realize that each vertex, so after each vertex is enqueued, so each vertex is enqueued at most once, right? It is enqueued only when it becomes white to gray, right? And also it's dequeued at most once, right? After it's dequeued, it will be painted black and it will never be enqueued again, right? And assume that the queue operation takes constant time, right? The queue, right? Yeah, the enqueue and dequeue operation all takes constant amount of time. So the total time for each for the total running time for all the queue operations would be big O of V, right? Because we have V vertices, and each vertex we enqueue and dequeue exactly once. So that will be the cost for the enqueue and dequeuing, right? And for the for loop at here, so that is the key component we want to analyze, right? So for the for loop, it actually scans the adjacency list for each vertex, right? But it's only do this scan only when that vertex U is dequeued, right? So that means each adjacency list is scanned only once, right? After U is dequeued, we will scan its vertex, its adjacency list. And after that, U is painted to black, which means it will never go back to the queue and dequeued again. So that is good news for us, right? We will scan the adjacency list exactly once, right? And now let's consider the fact, right? Since the summation of all the adjacency lists, or the summation of the length of the adjacency list, that's something we have considered in a previous lecture. It's either the number of edges or twice the number of edges, depending on whether it's directed or undirected graph, right? But anyway, we know it is at that level, right? It's either E or 2 times E. So the total time for the scanning scanning step is also big O of E, right? It's proportionate to the number of edges in the graph. All right. So putting that 2 pieces together, we have covered the enqueue and dequeue and the scanning process for all the adjacency lists. So the total running time would be big O of V plus E. Okay. And in graph algorithms, we basically need to use both the quantity of vertices and the number of edges together to describe the running time efficiency for a lot of algorithms. All right, that's BFS. So now let's look at the result of it, right? As we said, it creates a BFS tree, right? If we plot the roots, plot the source vertex as the roots, it will create a tree like this. And we can use the simple path from the roots to any vertex in the tree as the shortest path to represent the shortest path in a graph. Okay, so the path from S to W to X and to Y is actually the same, corresponds to the same path in the tree. All right, and something more about the shortest path. Okay, so it is the shortest path defined by the distance, and this distance is counted by the number of edges, right? So it finds a distance to each reachable vertex in the graph from any given source. Okay, so we can use the this delta quantity to indicate the shortest path distance. Okay, so this delta between S and V defined as the minimum number of edges in any path from S to vertex V. Okay, and sometimes when the graph is not very connected, it could be the case that there's no path from S to V, and in that case, this delta would be infinity. Okay, and the path length. So there could be multiple shortest paths actually. So if as long as a path is have this quantity, then it is one of the shortest paths. Okay, so there could be multiple of such shortest paths in a graph. Okay. All right. Oops. So on the next slide here, actually, this is not required, but how do we know that the BFS is correct? Like, how do we know that the Breadthfirst search algorithm, BFS algorithm, will compute all the distance correctly? So after the algorithm is done, the D attributes recorded in each vertex will be the theoretical shortest path delta S and V for all the vertices in the graph. So how do we know that? It's actually given by this theorem. Okay, but how do we prove this is not required. If you are interested, you can go to these 2 pages in the textbook. Okay, and next, the last question is about. All right, so after we have run the BFS, and it basically returns a tree, right? It records all the parent relationship between the vertices in the tree, right? So we can print the shortest path between any between the source and any vertex in the tree. So assume that we have run this BFS first. Then given 2 vertices, it's basically between the source S and V, and we want to print the shortest path, right? So we can basically write a recursive algorithm. If by tracing back from V to the parent of V, okay? So for example, in this case, if we want to know the shortest path, if we want to print the shortest path from say Y to S, right? And after we call this print path from S to Y, it will first check whether Y is the source, and of course it is not. So and if the Y has the no parent node, which means it is not reachable from S. And in other case, we need to call the procedure recursively by going to the parent of y, which is x in this case, right? And then calling print pass between s and x will also going back to the parent of x, which is w, and then going back to the s. But we know that the s will trigger the first if condition, right? Because now we are calling the source vertex again itself, so it will print the s. And after this s is printed, it will the recursion will return, right? It's the end, it's the boundary condition. So s will be first printed, and then we will print w, right? Then we will print x, and then we will print y. Okay, so that is the shortest pass principle procedure. All right, and let's look at, we have some time to look at the different version of searching algorithm, which is depth-first search. Okay, so I think it's a way to think of the search problem differently. Like in a Breadthfirst, we use a queue, right? We use in BFS we use a queue data structure to store all the gray vertices, right? Whenever a new vertex has been visited, we will paint its color from white to gray, and it will be in cubed. And then the loop will keep running until the queue is empty. But it's a different question now. Now, how do we go as deep as possible, right? After we have reached a vertex, then we want to follow that vertex and to go as deep as possible. So let's look at that way. Okay, so the strategy is to go as deep as possible, to search deeper in the graph whenever possible. Okay, and it will explore edges out of the most recently discovered vertex that still has unexplored edges, right? If that vertex has unexplored edges, we will stick with it. We will stay in that edge. We will stay in that vertex and goes deep, right? So once all these edges have been explored, then we basically need to trace back, right? We need to search backtracks to explore the edges leaving the vertex from which V has discovered. Like we go to the parent to see if the parent has other childs, right? So as a comparison with BFS, if we look at the DFS first, if we start from the vertex 1, then we may go to the vertex 2, right? But after 2 is visited, we do not go back to 1, but we will follow the we will look at 2 and to see whether it has unexplored edges. Like we can go from 2 to 4, right? And after 4 is visited, we will not go back to 2, but we will go back. We will go deeper to 5, right? And after 5 is visited, there's no edges going out, so we need to backtrack, right? Backtrack to 4, and then to 2, and then to 1, right? That will give us the another path, which is from 1 to 3. Okay. So in DFS, the sequence of being discovered for all the vertices is that 1, 2, 4, 5, and then 3, right? We go as deep as possible. And as a comparison, if it's BFS, it's just the Breadthfirst. Then if we start from 1, which means we will look at the distance of 1 first, we will make sure that all the vertices within distance 1 are visited first, right? So 2 and 3 will be visited. And then start from 2, we will look at 4 and 5 because they are within distance 2. Okay, so as a contrast, in this case, the sequence, the order will be different. The order of vertices will be different. It will be 1, 2, 3, and then 4 and 5. Okay. So a simple way, let's look at 2 simpler versions for DFS. In this case, first, the First way we define the DFS is to use a recursive style. Okay, and it's actually quite straightforward to write, right? So given a graph and a source vertex S, right? When we call DFS, we will first mark the visited attribute for S to be true, right? And we just need to go through the adjacent list for S. We just go through each vertex in that adjacency list of S, and if that vertex is visited, then we don't need to take care of it. But if it's not, if it's a new vertex, then we simply call the function recursively itself on that unvisited vertex, right? So in this case, we need to initialize all the visited attributes for all the vertices to be false, right? Okay, so if we look at the algorithm here, let's assume that we run the DFS recursive on the vertex U, right? So what it does is to look at the adjacency list, for U, right? So it will first mark the U.visited to be true, and then look at all the adjacency list for all the adjacency vertices for U, which is V and W, right? So let's assume that we will call the the first recursive call is on V, okay, and the second one will be on W, right? So within the first recursive call on V, we will basically paint the V.visited to be true according to the algorithm, right? And we need to go through the adjacency vertices for V, which is X and Y, right? And let's assume that we enter X again, and then X will be marked as true. X.visited will be true, right? And now we still need to go deeper by looking at the adjacency list for X, which includes Y, right? So Y will be visited, right? So Y, the Y will be visited as step here, right? So now let's consider the fact that after we returned from this recursive call, after Y.visited is listed, the Y.visited is modified to be true at this recursive call. So when we go a level upper, one level up, it will be this recursive call. But since now the Y.visited is already true, so this recursive call will not be executed, right? It will only be executed when this visited is false, right? So this one will not be executed, and we will need to go one step upper to that W, right? And when W is visited, we will also then we are done with the DFS search. Okay. All right. So I guess that is the first version of DFS, and we can look at a simple non-recursive or iterative DFS. Okay, so an analogy from the tree data structure or binary search tree, whatever tree data structure we have, is that whenever we don't want the recursive calls, then we should use some explicit stack data structure, right? Because a recursive call uses some implicit stack, right? It just uses a stack of the system, right? But we now can define some stack in our algorithm so that the recursive calls are cancelled, right? So in this iterative DFS, it basically does the same thing as the recursive, but now we use a stack. Okay, So assume that we have an empty stack, right? And we know that the push and the pop will add element to the stack, and the pop will remove the top elements, right? So this algorithm will keep run until the stack is empty, right? It will have a while loop running, and within the body of the while loop, it will pop the top elements, right? And it will check whether it's validated or not, right? If it is not validated, we will set it to be validated. And for each element in that adjacency elements, we will push it to the stack, right? So let's look at how this will affect the results. Okay, use the same example, for example, here, right? Remember that's DFS iterative, the same graph that we called with the recursive one. So let's say we call this iterative on the algorithm on the source vertex U, right? So U will be pushed to the bottom of the stack, right? So then the U will be popped, right? And it's not validated. So we will modify the validated attributes, right? And then we need to push the V and W back to the stack, right? And this order is arbitrary, right? We can, but of course it will affect our results, but it doesn't. It is not our main concern here. So we will push the V and W into the stack, right? We have V and W in the stack. So now since W is pushed later, so the W will be the next one being popped out, right? W will be popped out, right? And the V is the only one left. So W will be validated, and now the adjacency list of W will be scanned, right? For all the adjacency lists, all the adjacency vertex in W, they will be pushed into the vertex, right? So you see that now the X is pushed into the stack, but the V is still at the bottom, right? So that's how the depth first search is maintained, right? The element pushed in at earlier time will not be accessed at this point, right? Only the most recently validated elements will be accessed. Okay, so V will not be validated. Okay, so next iteration, X will be popped out, right? And X will be validated. And then the adjacency elements of X, adjacency vertex of X, which is V and W, V and Y will be pushed into the stack, and then assume that Y will be the next one being popped out, right? Y will be popped out and will be validated. And there are two V's, right? V is pushed in twice, but it's okay. So the next one being popped, nothing will be pushed in since Y has no adjacency vertex. So V will be the next one being popped out, right? It will be validated, right? And since V also has some adjacency vertex, which is X and Y. So according to the algorithm, they will still be popped in, pushed in. And now let's keep pop out elements since they are already validated, right? They will be keep popped out until the stack is empty. And then at this step, we are done with the DFS, right? So the results might be a little bit different from the recursive algorithm, depending on the sequence of how you define the way to pop in, to push in the adjacency vertices. All right. So in order to obtain the DFS tree, we need to basically do the same thing, similar work as the BFS. We need to record the dot pi, the parent attribute for each vertex, right? For example, we just put the whenever a vertex V is first validated, right? It will change the pi elements, the pi attribute to the source. Okay. All right. So in this case, the DFS recursive will return such a DFS tree, right? And it may be a different way to it may be a different tree to a different tree in a different shape with different architecture, different structure, because the way that we define the iterative will cause some difference within the of the tree without it. Okay. So that's two versions of DFS tree: DFS visit, DFS search, depth first search. So in the next lecture, we're gonna work on a more advanced version of it. So we will not only need to know the parents relationship between the vertices, but we also need to record the time steps, like at which time step we visit that vertex, and at which time step we have finished completed the visit for all the adjacency lists or all the adjacency vertices for that vertex. So that will be useful for some more advanced algorithms, right? When we later talk about topological sort, we will need to use that more advanced version for depth first search. Okay, so that means we will need to use more attributes for each vertex in the graph. All right, and I think that's it for today's lecture. And if you don't have questions, I will stop the sharing first.